Okay, great. Thank you again, Tanya, for the invitation to speak, and to you and EJ for organizing this. My name is Ben Brodsky. I'm the manager of the Chemical and Biological Sensors Department at Sandia National Laboratories. I'm classically trained as a chemist, as an organic chemist. However, I've spent most of my career actually in sort of the intersection between science and policy, particularly with respect to the intersection of science and national security. And so I've been here at Sandia National Laboratory since 2010 in a variety of different roles, and currently I'm the manager of this particular department. And so let's see, here we go. I'd like to start off my talk today with some acknowledgments. Again, thanks to Tanya and EJ for organizing this. This sensor rig concept is really cool, and it's very neat to see the research that's happening at UT Austin. I'd like to thank my the prior speakers as well for sharing their research. It's really fascinating. There are several colleagues at Sandia as well that I'd like to thank. Hannah and Nadine, I think, are on the call with us today from the UT Austin Academic Alliance team. And so I'd like to thank them for helping me prepare, as well as Tori and Steve, who offered me some helpful information as well. And of course, I'd like to thank my team, the Biological and Chemical Sensors team, past and present. It's a very large team. And I can't list everybody's name here, but as you can see on the right side of the slide, we're really an interdisciplinary team with core competencies both in science and engineering. And I should say on that note that my role as a department manager, I'm not a PI. My role is to help shape and implement a research strategy within Sandia, but frankly, I can't really claim credit for any of the technology that I'm going to be sharing with you. I'm really speaking on behalf of the Biological and Chemical Sensors team, but I'm very excited about the possibility of initiating some of these conversations, and I hope I can, alongside Nadine and Hannah, kind of serve as a conduit to some of the researchers at Sandia. And of course, thanks to all of you for your interest. What I'd like to do in the time that I have today is just give you sort of a high-level overview of what Sandia is as an organization. What is Sandia National Laboratories? And then also give you some examples of some of the biological and chemical sensor work that we've been focusing on, to give you just kind of a flavor of the type of research that we do at Sandia. It's certainly not comprehensive, but hopefully will at least give you an indication of the sort of problems that we go after at Sandia. So what is Sandia? Sandia is an entity that's known as a federally funded research and development center, or FFRDC. And there are a lot of FFRDCs across the country. Sandia is one of them, a very large one. And we are a government-owned, contractor-operated facility. And like other FFRDCs, our role really is to serve as a strategic partner to the federal government and a technical advisor to the federal government to advise and support missions of national significance. Sandia specifically, we focus on national security problems. Our work began during the Manhattan Project. That's when Sandia was established as an organization. And through the past 70 years, we have worked on various national security problems, a broad set of national security problems, kind of leveraging our experience in science and engineering. Our motto as an organization is exceptional service in the national interest. And so that's really where we try to focus our efforts as an organization. Sandia's work generally can be classified into sort of 5 different program areas in the sort of the national security space. I mentioned nuclear deterrence as one area, kind of where our organization began. But we have significant major lines of research and development in all 5 of these program portfolios, including global security, national security, energy and homeland security, and advanced science and technology. When it comes to chemical and biological sensors, that research tends to focus on problems in the energy and homeland security and advanced science and technology domains. But of course, there are multiple applications for these technologies, as I think we can all appreciate. So what I'd like to do now is give you just a few examples, as I mentioned, of some of the sensor research and development in the chemical and biological space. And I'd like to start off with an example from my department, focused on the development of microchemical sensor systems. For several decades now, in fact, we've been working on the development of these systems for various applications. On the left-hand side of the screen here is a picture of one microscale 2-dimensional gas chromatograph that our organization developed with support from DARPA. And the purpose of developing devices such as this is to create sensor systems that are low power, highly portable, low weight systems that demonstrate low rates of false alarms. And for national security applications, that's really important. We've developed the 2-dimensional microgas chromatograph because that offers the possibility of having two dimensions of separation of a complex set of analytes. If you imagine a sensor placed in the environment in a relatively complex, where an analyte of interest may be in a complex mixture with a number of other background chemicals, we've developed the 2-dimensional gas chromatograph as a means of separating analytes of interest from that complex background. And so this device includes what we call a smart pre-concentrator, which is essentially a resonator that's coated with a thin film that we can tune based on for example, we can tune its properties such as polarity based on the analyte of interest in order to selectively absorb analytes of interest and reject certain background chemicals. And then that pre-concentrator, once it reaches a certain threshold, can release its absorbed content into the microgas chromatograph, and it can go through those 2 dimensions of separation. Coming out of the gas chromatograph, we have investigated both internally and with collaborators a number of different detectors that can identify and characterize the analytes that are separated through the 2-dimensional gas chromatograph technology. On the right side of the screen here, I'm showing a miniature ion mobility spectrometer that our team developed, and we can couple these together to create portable chemical detection systems. So here's one example of how we are trying to apply this technology in the field. This is a project that was supported by ARPA-E. And one thing that we discussed earlier with Professor Anslin was this idea of using sensor technology to analyze volatile organic compounds for different purposes. And we're very much interested in using sensors to analyze VOCs, profiles that are produced by different organisms, including humans. And here I'm showing an example from plants, in order to use those profiles as an indication of state of health of that particular organism. And so in this particular project, we were interested in using the micro GC technology to analyze VOC profiles produced by different plants of agricultural interest in order to see if we could sort of correlate the VOC profile with different states of stress of the plant. And we were able to obtain at least some preliminary data that seems to suggest that we can see some unique VOC profiles there. Another sensor technology that we have worked on for a long time that I don't really have time, I think, to delve too much into, but we've worked a lot on developing microneedle-based sensor technologies as well as a minimally invasive sensor for diagnostic applications. In this particular case, we utilized microneedle-based sensors and applied those to different parts of the plant. And use those to look at the impedance, sort of the change in impedance of the plant as a function of the state of watering of the plant. And so in the top right here is a graph that shows two lines, and each line corresponds to a different location on a plant where a microneedle-based sensor was placed. And what you can see is the impedance response is strong in one area of the plant and not so strong in the other area of the plant upon watering. And so we're excited about the possibility of applying microneedle technology as again, a minimally invasive, non-destructive sensor platform for agricultural applications. I wanted to talk a little bit and give another example as far as Sandia's work in diagnostics for infectious diseases. This is a platform that actually was not developed by my group, but was developed by a sister organization at our California site. I should have mentioned, by the way, that Sandia has multiple sites around the country. Our main site's in New Mexico, where I am, but this technology here was primarily developed in California. And this is a platform that we call SpinDX. And SpinDX is a platform that was initially developed as an immunoassay platform, but molecular diagnostics can be performed on it as well, or nucleic acid-based tests can be performed on it as well. And what SpinDX takes advantage of is, if you can see on the image here on the left-hand side of the screen, you see sort of a compact disc with multiple microfluidic channels. And each microfluidic channel is individually addressable, and what SpinDX does is use centrifugal force in order to promote mixing of the reaction components with microbeads that are placed in each of those microfluidic channels. And what this allows is a diagnostic platform that requires very minimal sample preparation, because the centrifugal force that this platform applies actually separates the microbeads after reaction with the sample of interest through a density gradient, where the microbeads are collected at the bottom of, or sort of at the end, I guess, of the microfluidic channel. And you can kind of see that represented on the right-hand side of the image. And then at that point, the microbeads can be interrogated through optical means like fluorescence in order to kind of determine the reaction that occurred in the microfluidic channel. And so this is a platform that can be, is very flexible in terms of the types of assays that can be performed within the platform. And again, it has a multiplex capability as well. And on the right side here, I've listed a number of the use cases over the years that Sandia has utilized this platform to create assays for. And we've worked with a number of different external partners on sharing this technology. And just to wrap up, this is one example of a nucleic acid-based assay that can be deployed on the SpinDX platform. This is a lamp-based, a loop-mediated isothermal amplification nucleic acid assay that Sandia developed, called Quasar lamp. It's a particular form of the lamp assay that was developed at Sandia. And again, we've deployed this assay on the SpinDX platform, and this assay has some interesting advantages, including the ability to do multiplexing, as well as the ability to, in principle, deploy this assay in a resource-limited environment using tools such as smartphones in order to read out the fluorescence response from the reaction, and that's indicated here. So that's just kind of, again, a brief, I guess, sampling of different technologies at Sandia that we work on. In terms of kind of where I could see the potential for collaboration and further conversations. One thing I should note is that Sandia, we at a high level, we have very robust internship programs both at the undergraduate and graduate level, and we regularly bring interns in to join us and work with us on our research, as well as postdoctoral appointees. We also have some fairly advanced microfabrication facilities at Sandia that we leverage to develop some of the technology that I shared with you earlier. So I'm happy to get you more information about that. We're also interested in collaborations around chemistry, material science, some of the VOC work that I shared with you earlier. Some of the work that was presented during this session, was very interesting to me in some of those respects. And so, yeah, I think, very excited to continue this conversation. And again, I'd like to thank Tanya and EJ for the invitation. And I'll stop there. Thank you.